Hi there! After 3 months of break with my project about operating system on Rust for Raspberry Pi, I finally got time to get back to this project and do something on it. Meanwhile, I passed exam on operating systems course in university, read a bit more about operating system, have a better idea what I want to do with it. And in this video, I'm gonna cover the topic about making possible to write a driver, like about writing driver for Raspberry Pi UART interface. So we replace that QEMU output thing with a real hardware UART interface, and even more loading, like booting Raspberry Pi with our custom operating system. So it's kind of a kernel, not real operating system, it's just a kernel running on it and putting some text out in the UART interface. And to receive this interface data, I'll use UART like serial to a USB converter. There's a lot of different ones on the market. I don't know which one exactly we'll use, but the connection is pretty simple. If you're familiar with any Arduino-like microcontrollers, you'll handle it. Before we start, I want to mention again that I'm not expert in operating systems, neither expert in the Rust. I learned in both in the same time, and I use this video as a thing that keeps me accountable and makes more fun out of this learning process. If you have better understanding in the topic and you want to mention some mistakes or suggest a better solution, feel free to write this down in the comments, so I'll really appreciate feedback. So let's get to the business. First of all, I would like to mention again that I'm following mostly guides from this repository called Operating System Development Tutorials in Rust on a Raspberry Pi. They in their turn also following another tutorials from another repository, but that's how open source works. We learn from each other. So on the last video, I covered the topic with a safe globals, where we had a system output with a inferior, like interior mutability. We had a single instance of immutable thing where we could change some variable. In that case, it was statistics about how many characters we put into output. And in this video, I will cover what this tutorial number 5, like drivers, gpio, UART, offers us. Unfortunately, except this small description, there is no much explanation what code exactly does and how it works, except some rare comments there with explanation, but most of the understanding you have to do by yourself. Read this code, try to read some reference materials and try to understand this. And basically what it does, it just we throw out the magic QEMU console and use real UART interface now. The QEMU console is just an address in the memory where we wrote characters, and this address memory change always were put out to the our standard host machine std out. In this case, also here's some explanation how you want to run this on the real machine. My code you can find in this repository. Both links I will leave in the description. You can find and check out what I have there. Not much difference, almost nothing differs from this code. So let's go to the C line. The biggest changes happened in the BSP directory, which is board specific packages. And in this case, it's pretty much board specific because UART interface is a physical thing. It has certain address memory register addresses, and from board to board it will be different. Like there's a huge difference between a Raspberry Pi 3 and the Raspberry Pi 4. First of all, I want to mention this one. Here's like some configuration depending on which board we compile. The Raspberry Pi loads these drivers in. We have two drivers, not just UART interface driver, but GPIO driver as well. The reason is we cannot write the UART driver without writing driver for GPIO, because UART relies on the GPIO. And in this case, the specific board has and CPU has five or six UARTs, and in this case we use a single UART, and it's kind of a hard-coded thing. And if we go to this folder with BTM, stands for this name of this microcontroller CPU, not microcontroller but CPU, and it's a Broadcom core. And here we can find GPIO driver for that. And in the very beginning, you can find that we use kind of like the new dependency. You can find it as well here in the cargo toml file. It's called talk registers. Talk registers, it's a library from another operating system for microcontrollers. They cover memory mapping input IO. So when you have like physical something and you want to map this, so you have a more convenient way to interaction. So you do not work directly with physical addresses of the interface, but you work with a mapped addresses in memory of your system, which is what we want. We don't want to be very low level. In that case, it won't be a real operating system. It will be kind of a monolithic operating system with hard-coded things. It not differ from firmware at all. So the talk registers give us an abstraction on it and gives us methods to make it possible. And also here in the very beginning we have like descriptions taken from this and that. It's not only descriptions, it's also reference material. You'll have like two files, one from Broadcom and another one from Raspberry Pi documentation, and they cover basically all information about where and how you communicate with physical things in the SoC. So chip Raspberry Pi is pretty much the system on the chip, and this chip has UART interface, SPI interface, and this and that. And we need a reference materials to know in which registers we need to write what to get a certain result. And anyone who familiar with programming microcontrollers on low level, not Arduino scripting, but like C programming for STM32, for example, gives you a lot of familiar feeling, because you need to control directly registers, set a certain bits and bytes to certain values to get the result. And you need these reference manuals. For example, here you can find that this is chapter 11 UART interface, and it gives information about on which pins you can find UART interface, on which pins you can initialize it. Some UART interfaces can be initialized on the different pin outs. So if you already use some pins, you can initialize on the different ones. And here's some different registers. For example, DR, it's a data register, and it gives us addresses of like here's UART 0, 2, and here's different addresses for them. And also you can find a lot of like more detailed information will be on the on the Broadcom file. There's like more depth. You can read these reference materials by yourself, but basically what the author of this driver did, it took this information, packed this in the some constant structures, and use it in the function. For example, the interesting one is register block. It gives us access to most important for us, like read write input output things, and then and there is always will be a inner implementation and outer, so private functions and public functions. Publics obviously will be used in like public interface for rest of our operating system. And also this whole thing uses this mutex that we programmed in the previous video. It's allows us to be safe with working on these things, but there is also so-called unsafe initialization of the both drivers to make available putting some text out on the kernel panic. We can see it in the UART driver here. The same story reference materials a lot of can be found on the Raspberry Pi website. There is a documentation section where you can find a lot of information about hardware and firmware. And the same idea, working with a low-level thing, building an abstraction, so the rest of our operating system can use this. So, like data register, byte address, like reserved, not reserved, selection. So if this one allows us to turn on, turn off interface. And there is like a blocking, non-blocking situation. If we block in, we wait until all characters in the output TX buffer were written down to physical wire. This also used in the function flush. So when we block this, we call the function flush. We wait until everything is written down into the physical wire, and only after that write something. So therefore we use all our mutex and nulllock that we programmed, and this is like inner UART, and down here will be initialization of this driver and all functions that are available for the usage. And again, this statistics thing wrapped into the lock allows us to increment our written and read characters. You definitely need to read this whole thing by yourself to understand this. I read this like multiple times. It's still a lot of things to understand for me, but basically it's the same like if I would write some abstraction on the C to make initialization of UART on the low level with registers and passing this abstraction up to consumer of my library. All that done just in the Rust with wrapping this into the lock. Not super easy, but not like a rocket science, but not rocket science as well. So it's just like standard things, and these comments kind of self-describing. Yeah, kind of they say a lot, but still I would recommend to read this reference material as well. Then if we go to this console file that we already had in the previous video, it remains the same. This interface remains the same, but inner part is replaced with our UART interface. So in the previous video we had here like a huge code to work with a QEMO output thing, and now it's replaced with this one. And there's also another panic console thing that I already mentioned. This allows us to put text out when we have a panic kernel and we no more able to use secured, safe way like wrapped to the mutex UART thing. Also, there is a small change because working with the physical devices implies that we respect is like timing between send bits, bytes, and so on. We need also control on the timing, so how much kind of a wait and microseconds thing. And here in the Arch folder, in the Arch AArch65 in the CPU RS, we have this wait forever thing, And we have this new function called spin for n cycles. Using this function, we can wait for certain amount of the nanoseconds, microseconds, and so on, because we know kind of a frequency, like clock of the Raspberry Pi, and how many clocks cycles we need to do to wait for 1 second, for example. And this function is later on used in the UART driver, so it can wait until everything is initialized and so on. Later, basically, this console interface is everything that will be used in the upper level except the initialization. Also, there is a function called like drivers, the file called drivers.rs. This is a driver manager. This is interface through which we will interact with driver itself. So as you can see, there's a multiple abstractions, so physical level, driver for physical level, driver physical level, and another driver manager to initialize all these drivers and give an initializer and communication to the drivers for operating system. And this abstraction assumes and allows us to extend the drivers, so we can later on write driver for SPI interface, we can write driver for USB, for example, and so on and so on. And all these drivers will be available through this driver manager without any huge extension. So we would just add new drivers here, for example, and we would have like super USB, and that's it. And we also use this in the booting operating system. It can print out and tell us this and that drivers are available and you can do this and that, which is kind of cool. In the memory section, it's changed dramatically. Here we use this mapping, and basically it says it's a map of physical addresses to our memory. And where we define like initial starting point, which is different for different boards. You can see for board Raspberry Pi 3 and for board Raspberry Pi 4, the starting address differ, but offsets are same. So we just map these drivers to there. And if we go to the main, we can see what changed the most. The biggest change is here. So we have kernel initialization function and the main function, where we run our code. In initialization function, in kernel init, we basically initialize or attempt to initialize our drivers. If there is something goes wrong, we put this text out with panic, and at this stage will be taking attempt. So we don't have, we're trying to initialize UART interface and we fail initialize UART interface. In this case, this panic one will call this panic UART thing, so without any save things. And of course, if this doesn't work, we won't get anything, but there's a big chance that we will get some error output on the panic UART interface. Yeah, and when it's everything done, as it says, so println is usable from here and transition from unsafe to safe. In the safe part, we can use just safely our println, and so this println will put text out to the UART interface. And here's kind of a information. So here we'll put the name of our operating system version, or the name of a board, where it's all will be set. These variables will be set on the compiling time, and because it depends on the board, and then it will be just used in the runtime. And here we put out this one is already dynamic, and here will be all drivers that we have. So in this stage we have 2, gpio and UART, and if we will extend, then we will have more drivers, and then we get some charts written information, so the statistics. And the idea of this part is so we can put text with a keyboard in and we'll get out some text, but it didn't work for me at all. I don't know why, so I'll need to figure it out later. Yeah. So next step would be compilation, and to compile this, there's changes in the make file. We add some things to compile for real hardware, so you need to check this diff to learn a bit, and there will be another compilation target called miniterm. It's provided by this tutorial. It's just a mini terminal written on Ruby, allows us to communicate in a more convenient way with a serial device, serial to USB device. I'll cover this a bit later. So to compile this for Raspberry Pi 3, all thing that we need to do is to print make, and it will do the job. I already did this compilation, as you can see, and I have this file. And to put this onto the real machine, we would need a couple of files from Raspberry Pi firmware repository. And as this code says, we cannot load Raspberry Pi new operating system without having firmware for that. And these three files are necessary, and you can find them in the Raspberry Pi firmware repository. And these are closed source, so we don't know what's there, and basically we don't really care. Only thing that we need to do is to have SD card with a name boot, and we put our operating system, these three files from the Raspberry Pi repository, and the config file. Config file consists on these two lines. I don't know what this one means, that we use one core of the Raspberry Pi, and we set UART clock, so how will be clocked the UART interface. And all this information also can be found in the Raspberry Pi documentation section of the website, and there's a specific explanation how to use this config file. I also leave the link in the description. Yeah. And once you load this, and one more thing, this SD card should be formatted on FAT32. And once you've done this, you just eject this thing, take this card, just put in, and basically this is ready to run once you've done this. There is also explanation how to connect serial to USB connection converter to the Raspberry Pi. I'll leave also a link in the description. You just need like 3 wires. I have 4 just to connect also ground to another pin for my converter. It's specific for me, but I'm pretty sure you'll figure out it's not that complicated. And once we've done this, we need our terminal. And as I said, if we make miniterm, they will be started. I think I already put my once you run this, you'll see like waiting for dev/tty USB serial blah blah blah, and this is a specific name of USB to serial interface that I have. IO will be different, and I just put this as a default to not specify it every time. Of course, I could specify it just with a environment variable. And when I take this thing and connect this, sorry for not showing, I just put this connect this to the USB. Once I connect this, there appears a thing called like serial connected, and all thing that it says the serial converter is connected to the USB. And now I take USB power and connect to the Raspberry Pi. Once I connect it, it puts this text out. That's it, basically. So we have our name of operating system, version, booting on Raspberry Pi 3, drivers, BCM gpio, and UART. And it gives us written 124 characters. And now it assumes that if we put a text out in, it should put it out. I don't know why it doesn't work. I will figure out later. And that's it. Since I'm now familiar with writing a driver, kind of a copy-pasting a driver for a physical device, it will be also a good exercise and challenge for me to try to write my own driver. And I looking towards SPI, because if I will write driver for SPI, I'll be able to write driver for a small OLED screen which works over SPI or I2C. And this will allow us to have a kind of a screen output direct from Raspberry Pi without relying on this UART thing. This UART interface specifically will be used in the furthest, next steps to upload a new versions of operating system on the board. It's a chain loader. And it's great because you don't have to every time stick your SD card into the converter, adapter, put it into your PC, copy files, and again and again and again, just to test a new version. So just upload this and test. This is kind of a development toolkit thing. This was a second attempt to take this video, and I hope this time it worked better than previous, because I struggled a lot with sound quality and how I sound afterwards on the video, and it should be easier for you to follow my thoughts and what I mean in this turn. Let me know if it didn't. If you want more detailed depth, let me know also in the comments. Detailed depth, detailed dive into the code, what exactly each line does. I of course really can do this, but it will take about an hour, because I already did the video in this manner, but it's not listenable for true. I can do a stream with real lifetime questions and so on. Let me know, please, if you have any ideas or thoughts, please let me know in the comments. I really appreciate feedback again. And if you like this video, please consider subscribing, hit the like button, and ring the bell so you get notifications about new videos. And see you next time. Bye bye.